Hi, I'm Santiago, and this is an introduction to AI agents. So let me start with the question. How important will AI agents be in the future? My take is that we are starting a new technological era. And I want to share a couple of examples. The first is when we move from mainframes to personal computers. Mainframe was a rare commodity, only used by few large companies. And today, every single person has not one, but multiple computing devices. The second one is the internet. At the beginning, many years ago, there were only selected publications to distribute information at scale. Today, distribution costs are basically zero. Another example, a more recent one, mobile applications. A few years ago, we had a single hardware for a single application. In the case of the iPod, it could only play music. Today, with the iPhone, we have a million of applications, and we basically use it as a remote control with the physical world. We can order food, we can navigate, etc. And that's my take. Today, we use few algorithms, centralized algorithms, maybe content recommendators for social media, for Netflix, Spotify, etc. And maybe a few algorithms for navigation, Google Maps, Uber, etc. But our interaction with algorithms is very limited. And tomorrow, I think that we will be having, each person will have multiple agents at their disposal, each running with a personalized algorithm. Businesses will employ more agents than people, and many jobs will be centered around AI agents. That's me. What do you see? That's what I would like to hear. The authors of this paper go a step further and they start to envision an agent society where agents engage to each other and with humans to accomplish different tasks. And they even have bodies, so they can cook, they can plan, they can entertain, etc. That's their vision. And I think it's realistic, it's possible, certainly. So that's part of the motivation. But the second motivation for learning about AI agents is the economic opportunity. If we see this technological shift happening, then we might want to capitalize on it. And if we invest some time learning about it, then tomorrow we will start leading the implementation. And we can do this by building products, driving change, or simply seizing opportunities. So about me, I worked in big tech. I'm taking time before building my startup. And I started doing this because I want to listen to you, to exchange thoughts. I started reading a couple papers every week, and I got into it, and now I want to share it, but mainly I want to listen, to find different perspectives than mine. And also I took a few years ago a course in MIT about the challenges of global poverty, and it has inspired me about the potential of using technology to solve important problems. This is a new project, so please, if you would like to support it, please like and share. It's extremely helpful, especially now. And let's dive in. So what are AI agents? My definition, or probably the simplest definition, is robots without heart. They are like brains, thinking machines, quoting Doom. And they are composed by three main components: perception, reason, and action. Reason, a brain. We can go a bit farther. We can say maybe agents also have desires, beliefs, and intentions, always tied to the actions they need to perform. Or this is a last definition that it's a bit more technical, a neurosymbolic architecture. So the Miracle system is a system that has the power of large language models, but also of symbolic computations via APIs. Neurosymbolic architecture. This will be part of a playlist where today we'll be getting the basic introduction on how to build agents, the different components. But as we move forward, I plan to go into planning, prompting, reasoning, into memory and retrieval augmented generation, into how to use different tools and automation, and eventually going into multi-agents, communication between agents that is very interesting because they don't communicate as we communicate, and also hybrid collaboration, agent to human, machine to human collaboration. Other topics, maybe certain industrial applications where are agents already being used, which are the most promising areas. But I also want to hear from you. What other areas do you think are important? And I do hope that the composition of the audience, of the viewers, is varied, that it includes software, AI, business, investment, and people, ops, and management. So let's go into the basics. How to build an AI agent. This is the miracle system that I already provided definition. And we see here that it's like a workflow. It starts with the input text from the user, and this input is received by a large language model. Then we have a router that routes into different modules, and then we go into another large language model, or it can be the same, but another workflow with it, and finally the output text. So that's the basic architecture. And we see here that it has modules, different types of modules, different APIs to engage with the user. So in here they are having a weather API, if the customer is requesting the weather, a calendar, a currency converter, a calculator, etc. And within these models, the large language model can also be a model in its own right. So if the answer is better suited for a large language model, then it answers. It also serves as a fallback, because if the agent needs more context, more instructions, more details about what to do, then the large language model can engage with the human and specify the requirements. So a key part of this architecture is a router, because between the large language model and the models, there's a router that routes the different requests to the different modules. And what they are proposing, this is from AI Labs, from Jurassic, is that they train a specialized neural network. So they say this request is better suited for calculator, better suited for the weather API, etc. And they say that this advantage is that because they can train very cheaply. Every time they add a new module, they just retrain the router, but the entire architecture stays constant. So it's a very modular system that's easy to evolve. And another important challenge when using the Miracle is to extract the arguments, in this case for the APIs. So if we are using the calculator, maybe we are doing a summation, multiplication, maybe more complex operations. The human may provide those inputs in a wide variety of ways. Maybe in numbers, maybe in text, maybe with parentheses, without parentheses, etc., maybe, etc. And what they are proposing, and they provide an example on the paper, is to fine-tune large language models to extract that arguments. And they use data augmentation for this. So they use words, they use numbers, they create a lot of combinations from the type of inputs they expect to receive. And from them, they are able to extract the arguments, call the API, and then serve the results again through the large language model, supplying the additional context that they require. So that's an architecture. This was one of the first that was presented. Simple, elegant, useful, extensible, scalable, etc. And here are some of examples of the problems they solve. They say that their basic premise is that neural models are ill-suited for certain types of calculation. They say independently of how good large language models become, we will not be able to answer certain questions. And they provide here a couple examples, like the date today. The agent requires relevant information, up-to-date information, and another couple problems related to hallucination, because the large language model is not optimized for symbolic data. Let's go into a second architecture. This is a bit more sophisticated, but in a way it's also simpler to develop. And this is React, synergizing reasoning and acting in large language models. And they say that providing a reasoning enhances the large language model. In particular, they say that the definition of an agent is that it interacts with the environment and is able to perceive the changes in the environment. So the agent is able to make observations. And the agent can perform actions based on those observations. These observations can be requests from the persons, from the people. But they say we are augmenting the action space. So our agents not only act, they also reason, they also think. We are adding a new set of possibilities for our agents. And how they do it is relatively similar. So they also create, this is for demonstration, a simple module that is a Wikipedia API with 3 simple actions: searching, lookup, and finish. Lookup is like a control F. So if the agent is reading a page, it can go to the next sentence that contains the term that's important. And search, it searches the text, the term that is relevant, and in that sense, provides more context. So if the agent doesn't have the information to answer the question, it can fall back to Wikipedia and either search, go to the page, or find the most relevant pages. And finally, finishing. Say, we already have all the information that we have. Let's deliver it to the user. So here they are providing this example. And they compare it to other 3 examples. So the first is, the user is asking a question related to Apple Remote. And they compare it to standard answers, to standard Q&A, to chain of thought, which is a prompt engineering technique, and to a model that's only acting. These models are good for multi-hop answers, but they do not think, they do not plan, they do not have this perception, this reasoning layer. And here we see that the agent performs the actions that can be search, that can be lookup, that can be finishing, but they all, in the section of the right, it also thinks. It also refines their actions by thinking, by evaluating. So it's like an enhancement, a layer that enhances. And here we see the difference in the output, because through the enhancement, the agent is able to recognize the right search term. So that's the example. And this is very interesting because opens new challenges. When to think versus when to ask. They detect certain tasks that require thinking through every step, but other tasks that only require thinking seldomly. And here we see the example. Here we see that only occasionally does the agent think, and it still gets the right answer. So we get into all these subtleties. So those were 2 simple architectures, Miracle and React. What are some of its similarities? Well, from my perspective, both have this router functionality in the sense that the agent needs to determine whether to think symbolically via an API or think neurologically via a large language model. So that's a core similarity. The workflow is very similar. It involves a decision. There are some differences. The first one, the Miracle, is a bit more complex in what they are proposing. Their models also are more complex, but they require machine learning pipelines in itself, independent from large language model. The React architecture is simpler, as in the sense that it only uses large language model capabilities. To think, for example, the router is a large language model. And maybe we may also see differences in inference speed, because the Miracle is only performing one large language model request, while the React may be performing multiple, because it's able to multi-hop. So it thinks, it performs an action, and this action may require another thinking. So we see differences in latency And the other difference is that the React is potentially more self-aware in the sense, and potentially less prone to hallucinations because it has this enhanced action space that includes the thinking. And finally, what improvements? Of course, I would love to hear from you. What improvements would you think could be based from this architecture? From my perspective, I think this can be, I think the React goes in the right path, that it's starting to making the workflow more complex in the sense to cover more. And one of the first things that I would add is starting to think about parallel parallel threads. So right now the calls to the large language model are sequential. Maybe we can start thinking of parallelizing that. Another one could be adding memory to this. And the final improvement is in terms of maybe perception. Maybe we are seeing this React, but maybe the React can clarify the answers, can not only reason, but can clarify. So that could be some improvements at a simple glance that based on those two simple architectures. I will make a small pause to share a bit about the goals of this video. I hope to be able to build a community with other curious people that we can engage in Slack, where we can dream, share opportunities, learn together, share resources, and more importantly, hopefully even apply the technology to solve important challenges like climate change and global poverty. So if you want to help towards that goal, your testimonial sharing, if this is useful to you, it's extremely useful to share this video with friends. If you have other curious friends that are interested in this topic, please share and also give your feedback. I will get better with practice. I'm also not a native speaker, but your feedback is super welcome and super useful. And now I want to hop into the most possibly interesting part of this presentation, that is an exploration of human cognition. Because we cannot, at least that's my perspective, we cannot develop artificial intelligence if we do not first understand how we think. And this image is from the React paper, and they say that a unique feature of human intelligence is our verbal reason. Where our inner dialogue plays an important role for strategization, maintaining working memory, planning, etc. So let's start to think in here. And here, this is the paper that the React cite, and they say that our inner speech serves for four main purposes: memory retrieval and generation. So when we create memories, we decide which memories to create based, for some of us, in our inner dialogue. So if we keep remembering something, if we keep thinking about something, then this has a lot higher likelihood of being converted into a long-term memory, or at least medium-term memory. Similarly, for memory retrieval, we might remember something if we are thinking about something, if we want to think, if we have a certain problem, we might remember something, but we might think through it and maybe say, okay, this is useful, but we need another thing. We need some change. And during this process, it helps to retrieve relevant memories for our given situation. The second function that inner speech has is in planning and switching tasks. And of course, planning includes problem solving. Switching tasks is a bit more surprising, at least it was for me, but that's very natural. When we plan, when we have a complex problem, we need to think ahead. We need to think in different steps. We need to break down the problem in different pieces and find solutions and find a path that takes us from the place where we are to a place where we want to be. And the switching task, again, it was surprising because apparently there's a stream of thought that we use before switching tasks that prepare us to engage with the other task. Otherwise, we will be like starting to zero. And even more interesting is how they discovered this. Basically, they experimented with doing actions that involved our speech, our articulation abilities, and actions that didn't involve our speech, like tapping the foot. And we discovered that despite doing two different actions, only the ones that involved articulation that potentially harm our inner speech harm our ability to multitask. So if we are tapping our foot, even if it's at some musical rhythm or something like that, we are still able to switch tasks seamlessly. But when we are articulating, maybe when we are reading something, then we are not able to switch tasks as easily because we don't have that inner speech to prepare. The third use case for inner dialogue, inner speech, is social awareness. That's very normal. Sometimes it's not only, as part of our dialogue, is not only our perception, that plays a role, but also the perception of others. And we say, okay, what would this person think about this? What advice would I get from this other person? What happened during this other occasion? And that all plays into the social awareness, where our inner dialogue plays a crucial role. And lastly, also very surprising, is in motivation. They detected that a small percentage, as compared to the other tasks, but a small percentage of people, motivation played a critical role, both in their outputs, but also in their inner speech. So, and this happens a lot with high-performing athletes. When they are swimming, when they are running, when they are lifting weights, they are constantly repeating themselves. They are constantly pushing themselves to give more, to do more. And some use cases for inner speech. Now the question is, can we use some of these teachings for our agent? So let's say the first example I provide. What happens if an LLM is left alone running? We already saw on the React paper that when the agent is able to plan ahead, then we have this ability, then we have these improved responses. So what will happen if we leave the agent indeterminately? Maybe through 5 minutes, 10 minutes, maybe 50 iterations, 100 iterations, maybe until the agent determines that it already accomplished the task, etc. Would the answers improve? I would say that it's not for certain, but definitely there's a possibility if done right. And this also happens with us. If we give ourselves the first answer we think, it's usually not as good as if we think through stuff. So that's where we can start providing these agents with an inner voice to think about and iterate through complex problems. Second, and I already preluded a bit of this, foreshadow, parallel streams. But in this particular case, for creating a long-term memory. So let's say we are engaging with a typical chat application, and we engage all the time with this chat application. Sure, the agent could start remembering every single conversation, but that might not be the most useful thing, because there are things that are more important to us than others. Maybe we just wanted a synonym, and that conversation can be easily discarded. However, maybe we were engaging in a deep engineering topic, and we want to start right where we stopped the last time. And this is where building this long-term memory works. So what will happen if, just as we are engaging with the agent, there's a parallel background process that starts to evaluate which pieces are relevant to store long-term and which ones not. And even maybe start thinking of suggestions, maybe start thinking of shifting and providing useful information to the main thread that is engaging with us. So we can start seeing how these diverging possibilities could help the performance of the agent. And the third possibility, and I hope to hear from you, but these are only some of my ideas, is, can the agent develop a personality, beliefs, and intentions based on their assigned goal? We already saw that definition. And why I say this is possible? Because our personality because it's useful for certain roles. So if we are in customer support, we might be friendly. If we are in security, we might be very preventive. We might be very risk aware. If we are in sales, we might need to be very proactive. And in such, and personality is only part of memory. I mean, there are other factors that influence it, but memory plays an important role. So can the agent start to iterate on who the agent is, how the agent communicates with the person through this inner dialogue? Could it have some sort of self-awareness that evaluates their results based on their interactions and starts to find that optimal personality to serve the humans? Is it a possibility? I definitely think so. And similarly with beliefs, like there are certain beliefs that are good for certain tasks, and it can evolve the beliefs. And in that sense, the agent can start developing conviction. And there is in some ways that the agent will be open to the customer requests, but there are other parts where are important to the agent that they will not be open because the agent has the deep belief of something being true. And similar for intention. Maybe this is an agent that helps researchers explore different topics. So in this case, a very curious agent would be ideal. So those are some of the examples of how can we use this inner voice, inner cognition to ensure an agent. I want to provide a second example of how human perception, human cognition can help us develop better AI agents. And this is in sensing and perception. In this image from Stanford, we see the difference between sensing and perception. We see that sensing is raw data, while perception has already meaning assigns meaning to objects. So what before were just lines, edges, points, now it's desks, screens, a conference room, a trash can bin, a desk, etc., bookshelf. And similarly below, the image is cut, sorry for that, but we see the same for a dynamic environment when using self-driving. So that's the difference between sensing and perception. How useful is that? Before, I mean, I think it's obvious how useful is that. We could not train an AI agent to self-drive just alone by sensing. We need to perceive as well. We need to infer if this is a line change, if we need to stop, etc. And I want to illustrate how complex perception is, because in the image it appears to be very simple. But in terms of visual perception, this is a 5-step process that starts in the retina when our cones are receptive to specific wavelengths, 3 in particular, red, green, and blue. And these wavelengths through signal processing are used to create a rich palette of colors. And then segment colors that are next to each other into similar regions. This is image segmentation. With that, a visual map is created in the visual cortex at the back of our mind that emulates what we are seeing, but in our mind. And from there, we can start to recognize lines and edges that we transform into features and objects. We are almost there, but we need more complex algorithms to perceive depth and motion. For that, it's very important that we have binocular vision because we are able to see slightly different frames, and that we are also living in a 3-dimensional space, so that we can infer that based on shifts on color, we can infer depth. And during this process, we are engaging with memory, language, and cognition to derive meaning from what we are seeing. So this is an example of how complex perception it is. And this is why I think it's an extremely important problem for artificial perception. Instead of plainly acting with the human cognition, with the person, we may want to enrich that context, that information that the user is providing us with additional context. So for example, if we get a request, then we might want to retrieve when have we faced this request in the past, and when have we gotten a successful interaction, and when haven't. Maybe we can engage with previous interactions with this same user to understand, okay, is the user looking for professional information or maybe more for entertainment, personal information? And those types of perceiving, of extracting the intention, the meaning behind the ask, could be a very could be a very rich source of information to improve the agent's performance. And here are my 3 predictions on artificial perception. The first is that perception will be the most valuable problem to solve when building AI agents. I think I already explained it, but I want to add 2 factors more. The first is that we have this 3-step process: perception, reasoning, and action in an agent. The cognition part, the reasoning part, is mostly handled through large language models. And as far as we are seeing, this is a layer of the stack that is mostly being commoditized. There are very small differences across very large layers. It's not where a lot of value will come from. The action part is reusing existing software. We see that the action is through APIs, and we already have a lot of that stack. In part, what makes agents are so useful is because they integrate so seamlessly with our existing architectures. But the perception layer, that's where, from my perspective, the magic happens, because that's the part that may require to be adapted within each task. That part will need the most creativity. That part requires the most domain expertise, and that's the part that's the most variable. So that's my first prediction, that perception will be the most valuable problem to solve when building AI agents. The second is that perception will not be solved using large language models. And this is because large language models are limited. They have a limited context. They are not parallelizable. They just predict one token next to each other. And also they are relatively expensive, require specialized software. And if we compare all those shortcomings to the amount of information we need to process to perceive, comparing, for example, in the sense of perception in the visual system, a large language model will not be able to handle that volume of information efficiently at the speed that it needs to create meaning. And in that sense, I think more traditional machine learning methods, sure, maybe aided at some points by large language models, but will be able to deliver this meaning that we are looking for. And the final one is that a new language representation is required to perceive language at scale. This is extremely important and very difficult to see, because we are able to perceive because we live in a 3-dimensional environment with a binocular vision. But today we are able to process language because we have developed a speech at a certain speed. But that speed needs to drastically change to incorporate a torrent of information and be able to perceive just as we can create meaning from visual perception. And that would be extremely challenging without a new architecture. I do have some ideas of how this architecture would look like. I would be happy to share in the comments. And this is the last topic, I promise. Thanks to you for staying till the end, which is space representation. And this is fascinating topic that says that an agent represents our minds represent the space as a graph. So where nodes represent objects and edges proximity and orientation to other objects. So this is very different from the pixel representation that might be more intuitive. Instead of saying this as a continuum, we are saying this as a discrete process where we approximate. And this is how our spatial navigation memory works. So why is this important? Because this is very different to how databases operate. Our spatial memory is very different. The first difference is that we store different spaces in the same graph. When we represent a new object, we use an entirely new representation. When we grade, for example, if we are representing a text, we do not overgrade the same text in the previous text. No, we use different pieces of paper, different bits of information to represent the same graph. The second very important benefit of this is that new spaces are combinations of previous spaces. And this is extremely helpful for recommendations because instead of all the spaces, all the objects in a database being relatively similar to each other, each has their own primary keys, etc. I'm sure they might have some categories that are shared the same, similar foreign keys, etc. But there is no concept of similarity, which is natural in this representation because new spaces are combinations of previous spaces. So if we encounter a new space, what our mind immediately thinks is, this place looks similar to this one that I already was. Next, and this is of course useful for recommendations. This is already what I preluded a bit, because what's changing between different spaces is only connectivity. This makes it very simple to update different spaces. When we update a database record, we might update certain fields, but what happens when what we are representing is very large, like for example, a space, which is continuous, which has a lot of information, and what happens if we move an object, then updating in a database where it could be a map of bits is not that easy. But if we are in a space and we want to update an object, it's as simple as moving the object. Simple as that. And the final one, applications useful for embeddings. This is extremely difficult to see, but today our embeddings are basically either arrays. But what would happen if we start to represent these objects dynamically and in a chart oriented? This opens possibilities of how we engage with embeddings and how we understand embeddings. I will not dive deep into this because this could be a topic in its own self. This could be a research paper in itself. But, and this is the last slide, what I do want to say is that from here it emerges a very interesting concept, that is identity. Because within this spatial graph, there's a particular node that represents us. So we have the space and there is a node that is us. And these nodes form connections, just as every other node forms connections with emotions, memories, and meaning. That means that we have a meta representation about ourselves. We think about ourselves in a specific way, attached to emotions, memories, and meaning. And this representation is not our entire concept of identity, but it definitely plays an important role. And my point is, what happens if we provide this meta representation to the agent to endow them with personality? So we say, okay, this is your worldview, this is your memory, but within this memory, there's also something called you. And this is who you are, and who you are is evolving. Going back to a few slides ago, this is how we can start providing agents personality, intention, beliefs, and this is how we can hardwire that into the agent itself. So thank you. I know this was a lot. I'm really appreciative you managed to went into the end. The next video will be in approximately 2-3 weeks, and it will be about prompting, planning, and perception. I hope I see you there, and again, thank you for being here. Goodbye. That's the bibliography. There are three papers related to agents. One of those is a survey, which I took a couple images from there. 3 papers about human cognition. Very recommended, the 3 of them. The third one is in the middle between human cognition and robotic embedding agents, but still extremely interesting. And the final, there's a very useful introduction for LLM power agents by Lilloch. There's also one image from there, and I recommend you reading. It also provides a couple examples, more reference for you to see. Thank you. Goodbye.